Hello students, I hope that you are good, well and fine. In today's session, we will be beginning chapter 12, linear programming. Okay, so we will be understanding what do we mean by linear programming, what are the applications of this linear programming as you move forward in this chapter. As we move forward in this chapter, you will notice that this is quite interesting topic in itself, that it gives you the how to maximize your things, how to minimize your things. Okay, you will be able to answer how to maximize any output. Yes, how to maximize anything you want. Okay, not anything actually. Okay, and how to minimize your expenditure, how to minimize your what other stuffs. Okay, so you will know that what you can do from using this chapter, linear programming. Okay, so let's see. So for example, a furniture dealer deals in only two item, table and chairs. He has 50,000 to invest and has a storage space of at most 60 pieces. A table costs 2,500 and a chair cost 500 only. He estimates that from the sale of one table, he can make a profit of 250, and from the table of one chair, he can make what? 75 rupees. So he wants to know how many tables and chairs should he buy from the available money so as to maximize his total profit, assuming that he can sell all the items which he buys. Such type of problems which seek to maximize or minimize profit or cost form a general class of problem called optimization. So this chapter mainly gives us the tool, or yes, tools for optimization. Okay, thus an optimization problem may involve finding maximum profit, minimum cost, or minimum use of resources. Okay, so I hope now you are able to see that what are the application, or what is the class of application you will have after, or just throughout this whole chapter, linear programming. You will be optimizing your things, you will be maximizing your profit, you will be minimizing your investment. Yes. Okay, so let's jump to our terms and terminologies related to this chapter, so and understand the topic in depth. So linear programming problems and its mathematical formulation. So let's see how we formalize our things. So we've as for example, so let's start with the example. So as we just saw an example, dealer can invest his money in buying tables or chairs or combination thereof. Okay, further he would earn different profit by using different investment strategies. There are certain overriding conditions or constraints. Okay, so his investment is limited to a maximum of rupees 50,000, and so is his storage space, which is for a maximum of 60 pieces. Okay, suppose he decides to buy table only and no chairs, so he can buy how many tables? So as you can see, just only 20 tables. Yes, as each table costs him about 2,500 rupees. This means he can only able to buy 20 tables, and his profit will be what? For each table he sold, he will get back 250 rupees. This means 20 table. Now for each table he will be getting 250 rupees. This means multiply with 20, you will have only 5,000 profit he will be gaining. Okay, now he chooses to buy chairs only, then so one chair costs him 500. This means in total he can get 60 pieces. He can get 60 pieces. Now if he purchased he bought 60 pieces of chairs, and for each chair he will get a profit of 75 rupees. This means 60 multiply 75, in total he will gain 4,500 rupees. Yes, as you are seeing the difference. Okay, difference of 500 rupees. Okay, so there are many other possibilities. For instance, he may choose to buy 10 tables, 50 chairs, as he okay, so as he can store only 60 pieces, the total profit in this case would be what? 6,250. Yes, as you compare from the above profits, you can see that comparatively it is greater than the before ones. Okay, so such kind of problem, such kind of things you have to tackle in this chapter. You have to maximize your profits, minimize your input or expenditure or the cost, whatever you wanna call it. Okay, obviously if you give the dealer these 3 points, he will be go with this, the last one, the third one, as he will be getting back 6,250 rupees. Yes, or the if you try to get the whole idea of the optimization, okay, using the tools you will be just about to learn. Okay, so he will choose the maximum where he is getting the maximum profit. Okay, clear? So I hope that it is very clear to you, and now you will have an idea about why it is very important from the perspective of optimization of your things. Now, mathematical formulation of the problem. Let x be the number of tables and y be the number of chairs that the dealer buys. Okay, obviously x and y must be non-negative, as you cannot have negative numbers of tables and negative numbers of chairs. Okay, either you can have your no tables or no chairs, or some number of tables, some number of chairs. This gives you the mathematical formulation of, or a mathematical inequality, which says that x must be greater than equals to 0 and y is also greater than equals to 0. Clear? Okay, I hope that it is clear. Okay, now the dealer constraint by the maximum amount he can invest. So the maximum amount he can invest is 50 rupees. Okay, and by the maximum number of items he can store is 60. This means the sum of chairs and table must be less than or equal to 60. Okay, I hope it is clear. And investment constraint will be, as for each table he have to spend 2,500, and for each chair he have to spend 500 rupees. This means in total 2,500x plus 500y must be less than equals to the total investment, which is 50,000. Okay, this gives, if you divide both the side from 500, you will get 5x plus y less than equals to 100. So now you will be having 4 inequalities, 2 from here and 2 from here. Okay, so clear? So these are the pieces of information already given to you. You have extracted from your problem. Okay, now dealer wants to invest in such a way so as to maximize his profit, say z, which is stated as a function of x and y, is given by z is equals to 250x plus 75y. Okay, we call this function as your objective function. We call this function as your objective function. Okay, clear? Okay, I hope it is clear to you. Now what is happening? Let's try to see. Okay, Now, mathematically, the given problem now reduces to maximize this thing. Yes. Now, your what? Now your problem is reduced to maximize this z is equals to 250x plus 75y. Subject to what constraint? 5x plus y less than equals to 100, x plus y less than equals to c, x greater than equals to 0 and y greater than equals to 0. Okay. Clear? I hope that it is clear to you. Okay. So in order to maximize his profit, okay, z, which is stated as a function of x and y, given by this, okay, it is already given by this, we call it as an objective function. We call it as an objective function. Okay. Now these are the constraints. So now we have to maximize the linear function z subject to certain conditions determined by a set of linear inequalities which with variables as non-negative. There are also some other problems where we have to minimize a linear function subjected to certain conditions determine a set of linear inequalities with variables as non-negative. Such problems are called as linear programming problem. Such problems we will be calling it as linear programming problem. Thus, a linear programming problem is one that is concerned with finding the optimal value, maximum or minimum value of a linear function called objective function. You just saw your objective function already given to you of several variables subject to the condition that the variables are non-negative and satisfy a set of linear inequalities called linear constraint. Okay, so the conditions given to you we will be naming or calling it as linear constraints. The term linear implies that all the mathematical relations used in the problem are linear relation, while the term programming refers to the method of determining a particular program or plan of action. Okay, clear? Okay, so now let's see objective function. A linear function z is equals to ax plus by, where a, b are constant which has to be maximized or minimized is called linear objective function. So any expression or any function of this type, we will be calling it as a linear objective function. For example, in the above example, this z is equals to 250x plus 75y is a linear objective function. Variable x and y are called decision variables. Okay, as the decision depends on x and y. Yes. Now constraint. So what do we mean by constraint? Constraints the linear inequality or equations or restrictions on the variables of a linear programming problem are called constraints. So constraints are just nothing but restrictions, conditions, inequalities. Okay, so clear? I hope it is clear to you. Okay. Now optimization problem, a problem which seeks to maximize or minimize a linear function, okay, subjected to certain constraints as determined by a set of linear inequalities. We will be calling it as an optimization problem. We will be calling it as an optimization problem. Okay, clear? I hope it is clear to you. Now let's see the graphical method of solving linear programming. Okay, sorry. So what? So the graphical method is quite simple. So let's see. So the constraint you are having just what? So constraint you are having are 5x plus y less than equals to 100, x plus y less than equals to 60, x greater than equals to 0, y greater than equals to 0. The graph of this system, if you find this graph, consists of the points common to all half planes determined by the inequalities. Each points in this region represent a feasible choice open to the dealer for investing in points and in tables and chairs. The region therefore is called the feasible region. Okay, every point of this region is called a feasible solution to the problem. I hope that it is clear. What do we mean by feasible region? Region where the points, if you apply those points, you will have the all the constraints satisfied, okay, and or the possible candidates for the solutions. Okay, as you can see, the common points for all of the inequality, all of the restrictions, you will have this blue shaded region. This we will be calling it as a feasible region, and these points contain in this blue area, we will be calling it them as a feasible solution. Okay. Now let's see. So feasible reason, the common reason determined by all the constraints, including non-negative constraints, as we just saw. Feasible reason. Okay, clear? I hope that it is clear. Now the area or the points where you are having outside this blue region, we will be calling it as infeasible reason. Reason other than feasible reason, we will be calling it an infeasible reason. Okay, feasible solution points within. So feasible solution means points within and on the boundary of the feasible reason represent feasible solution. Okay, clear? Okay, so if you refer this figure, every point within and on the boundary of the feasible reason OABC, you will okay, so every point within or on the boundary of the feasible reason OABC represent the feasible solution of the problem. For example, the point 10, 50 is a feasible solution of the problem. So are the points 0, 60, 20, 0. Okay, clear? Now, any point outside the feasible reason will be an infeasible solution. For example, 25, 40. Okay, so if you refer 25, 40 will be somewhere here outside this feasible reason. This means an infeasible solution. Now, optimal or feasible solution. Any point in the feasible reason that gives the optimal value or maximum or minimum value of the objective function is called an optimal solution. Okay, so optimal solution means the any value which gives either the maximum or the minimum value of the objective function, we will be calling it as an optimal solution. Okay, now let's see a theorem. So let R be the feasible reason, okay, for a linear programming problem, and let Z will be your objective function. When Z has an optimal value, that means maximum or minimum value, where the variable x and y are subjected to some constraints described by linear inequalities, this optimal value must occur at a corner point or vertex of the feasible reason. Okay, clear? I hope that it is clear. So whenever you have a feasible reason, convex polygon, whenever you have a feasible reason, this means the essence of this theorem says that you must have your optimal value at a corner point or a vertex of the feasible reason. Okay, now second theorem says R be the feasible reason, okay, for a linear programming problem, and let Z is equals to ax plus by be the objective function. If R is bounded, if your reason is bounded, okay, that means some enclosed area, then the objective function Z has both a maximum and a minimum value on R, and each of these occurs at a corner point vertex of R. Okay, now if R is unbounded, then a maximum or a minimum value of the objective function may not exist. You will see. If it exists, it must occur at a corner point. So in total, what you will get back is that your maximum or your minimum points or the solution, feasible solution, will be at where? Your optimal solution will be at where? At some corner point. Okay, okay. So in the above example, the corner points, the vertices of the bounded feasible reason OABC, okay, corner points are OA and BC, and it is easy to find their coordinates as 0, 0, 20, 0, 10, 50, 0, 60 respectively. Now compute your objective function values at these points. You will have at O the value will be 0, at C value will be 4500, at B value will be 6250, at A you will have 5000 as your profit. So this means your maximum output will be this, or the optimal solution will be 1050, 10 tables 50 chairs. Okay, a corner point of a feasible region is a point in which region which is the intersection of two boundary lines. Okay, a feasible region of a system of linear inequality is said to be bounded if it can be enclosed within a circle, otherwise it is called unbounded. Unbounded means that the feasible region does extend indefinitely in any direction. Okay, clear? Okay, so the answer to the above optimal problem was buying 10 tables and 50 chairs. This method of solving linear programming is referred to corner point method, and the method comprises of the following steps. Let me just once again go through the corner point method. Okay, so find the feasible region. Okay, so first point is to find the feasible region. Determine its corner points, okay, by inspection or by solving the inequalities, and then evaluate the objective function value at each of the corner points. Okay, and now identify what will be your capital M and small m. Capital M means largest or maximum value, small m means minimum value. Okay, when the feasible region is bounded, M and M are the maximum and minimum values of Z. In case the feasible region is unbounded, we have, okay, so clear? Now fourth, M is the maximum value of Z if the open half plane determined AX plus BY is greater than MM has no point in common with the feasible region, otherwise Z has no maximum values. And similarly, M is the minimum value of Z if the open half plane determined by AX plus BY less than M has no point in the common with the feasible region, otherwise Z has no minimum value. Okay, we will now illustrate, let's see some examples of corner point method. Okay, so let's see example 1. Solve the following linear programming graphically. So maximize this objective function constraint subject to constraints. These constraints: x plus y less than equals to 50, 3x plus y less than equals to 90, x and y both are non-negative. Now if you shade or if you find the feasible region, you will have this. Okay, you can easily draw this graph, okay, for these inequalities. Very easy, we have already seen in previous classes. Now you will have your feasible region as OABC, and you can easily see that this is enclosed, this is bounded, and the corner points will be what? The corner points will be the intersection of your lines given from these: x plus y is equals to 50, 3x plus y is equals to 90, x is equals to 0 and y is equals to 0. So you will have what? O 0 0, A 30, 0, B 20, 30, C 0, 50. So 4 points, 4 corner points. Now find out the what value of the objective function. So you will have at O you will have the value 0, at A you will have 120, at B you will have 110, at C you will have 50. So you can easily see the maximum value is 120. This means at point A the feasible solution will be 30, 0 of the optimal value, optimal solution, where you will get your maximum output as 120. The answer will be 30, 0. Clear? Okay, now second example. Second example says solve the following linear programming. Solve the following linear programming. So minimize this objective function subject to these constraints. So first of all draw your lines, and according to the inequality draw the feasible region. As you can see, the feasible region will be ABC. Okay, this is bounded. Corner points 0, 5, 4, 3, 0, 6. The values at these corner points of the objective function will be for 0, 5, 2500, for 4, 3, 2300, for 0, 6, 3000. As you can see, the minimum value is 2300, and the minimum value you are getting on what point? At B point. So the minimum will occur at 4, 3 point. Okay, clear? I hope it is clear. Now example 3. Solve the following problem using the graphical approach. So minimize and maximize z equals to 3x plus 9. The subject to the constraints x plus 3y less than equals to 60, x plus y greater than equals to 10, x is less than equals to y, x is greater than equals to 0, and y is greater than equals to 0. So from the inequalities you get your bounded region. Okay, A, B, C, D as your feasible region. The corner points will be A 0, 10, B 5, 5, C 15, 15, D 20, 0, 20. Now find the values, the corresponding values of the objective function. So at corner A you will have 90, at corner B you will have 60, at corner C you will have 180, at corner D you will have 180. So the minimum value is 60 occurring at 5, 5. Maximum value is 180 occurring at 2 points 15, 15 and 0, 20. Here it is already given that your x must be less than y, if you see. So x must be less than y, or can be even same as y. So C and D will give you the maximum output. It is follows these. Okay, so now what? Now if you try to see what is happening, so now the minimum value will occur at 5, 5. Okay, clear? I hope that it is clear to you. So the maximum value will occur at 2 points, and the maximum will be 180, and the minimum value occur at 5, 5. The minimum value will be 60. Clear? Now remark. Okay, so observe that in the above example, the problem has multiple optimal solutions at the corner points C and D. That is, the both points produce same maximum value 180. In such cases, you can see that the every point on the line segment CD joining the corner point CD also give the same maximum value. Same is also true in the case if the 2 points produces same minimum value. Okay, so this means you can have your multiple optimal solution. Okay, clear? You can have that situation also. Now next example. So objective function is given in this form, the constraints given in this form. You will have your feasible region, as you can see here. Okay, and your feasible region is unbounded, as it is going in this direction indefinitely. Okay, so now you have to first of all identify or determine your corner points. You will have corner points as what? 1, 0, yes, 6, 0. So 1, 0, 0, 3, 0, 5, 1, 0, 0, 3. Okay, and 6, 0. Clear? Okay, 1, 0, 0, 3, 0, 5 and 6, 0 are the only 4 corner points, as you can see. Yes, 4 points A, B, C and D. Clear? I hope that it is clear. Now the maximum, the values corresponding to the corner points will be 0. For 0, 5 you will get 100, for 0, 3 you will get 60, for 1, 0 minus 50, for 6, 0 minus 300. So minus 300 will be your smallest value. This represent what? So the optimal solution or the minimum will be minus 300 occurring at 6, 0 point. Now, okay. So the smallest value of z is the minimum value of z. But here, if you try to see that the feasible region is unbounded, okay. Therefore, minus 30 may or may not be the minimum value. Okay. So minimum value of z or means minus 30 may or may not be the minimum value. So to decide this issue, we graph the inequality. What? Minus 50x plus 20y minus less than minus 300. Okay. So you will get minus 5x plus 2y less than minus 30. Okay. From here, what you can check is whether the resulting open half plane has points in common with feasible reason or not. If it has common points, then minus 30 will not be the minimum value. Otherwise, minus 300 will be the minimum value of z. As shown, it has common points. Therefore, as you can see, okay, it has common points. Yes, which shows that therefore z is equals to minus 50x plus 20y has no minimum value subjected to the given constraint. Okay, clear? Z is equals to minus 50 plus 20y has the maximum value 100 at 0, 5. Okay, so in order to get this answer correct, you have to explore by your own that check for this thing that minus 50x plus 20y is greater than 100 has common points in common points with the feasible reason. Then the same logic will be applicable here. Okay. Now the last example we will be seeing here. To minimize this, z is equals to 3x plus 2y will be our objective function. Constraints are here. Now just graph it. After graphing, you will get what? This. Okay, clear? And as you know that, so from here, what you can say is that your reason, where is your reason? As you can see, so from these inequalities, if you try to graph it, okay, you will have what? If you try to graph it, you can see that there is no point satisfying all the constraints. So you do not have a common reason where all the constraints are satisfied. As x plus y is greater than equals to it, this represent this shaded region, this lightest blue region. Okay, 3x plus 5y is less than equals to 15. 3x plus 5y is less than equals to 15 shows this. Okay, and I hope that it is clear. Okay. Now what is happening? So this means what? You are having no common points where all the constraints satisfy simultaneously. Thus the problem is having no feasible reason and hence no feasible solution. Okay, clear? I hope that it is clear why we are saying that it is not a feasible solution. There exists no feasible solution. Okay, so far so good. Okay, so this is it for now. We will be back with the NCERT exercise 12.1. So for now, this is it. So thank you all. We will be back again with more interesting problems from this chapter, linear programming. Again, thank you.